Welcome to the Introduction to Calculus. I'm Mr. Stark. Thanks so much for joining me. Really appreciate it. I hope you'll stick with me through the entire video series. Before we get started, I'd like to talk about the agenda that's in front of you and then some of the how-tos below. So first, the agenda. There's a column for days that tells you about how many school days we would usually spend on this topic. So the first two topics would take a full school week. In the summer, it's a little bit different. The section is just the section that corresponds to the textbook I use. There are 4 topics. The tangent problem is something we focus on very early on in the course. And in Calc AB, we start talking about the area problem in the second semester, but for Calc BC, a little bit earlier. Then the dates column, that's just an open space for you to schedule your time to watch the videos. I mean, you could probably watch them all in one day, but that might be grueling. So you could schedule your time. And finally, the notes. I just tell you how many videos that there are for each topic. So topic 3 has the most videos, and it's just broken down into 3 bite-sized pieces. If you're watching this video, you know how to access the video lessons, so I won't talk about that. But how to watch video lessons. I put watch in quotes because you're not just watching me do math, right? You'll sit at a table with your pencil in hand, booklet in front of you, taking notes, and have a TI-84 available just in case I use it. Probably the most I'll use it is in topic 4. Finally, for how to practice. Now, during the school year, you have your teachers that are encouraging you to do the practice. But if you're watching this video on your own time, then that means you need to decide to do the exercises. So if you just watch me do math, that's one thing. If you watch and take notes and pay attention, that's better. But the best thing to do is to follow that up with some exercises. So try some of those, evens, odds, whatever. I'll give you some hints, or actually I'll write it in the description as to which exercises correspond to each video lesson. So that should help you. And then the answers are in the back of the booklet. But if you get stuck, you don't know how to start, you don't know how to get to the answer, or if you have any general or specific questions, then just let me know. Comment below or send me an email directly. Let's get started by talking about the slope of a parabola. Here's a parabola. But wait a second, I thought lines had slopes. Like the equation y equals mx plus b, m is the value of the slope. How could there be an equation that shows a constant slope for a parabola? Well, let's not worry about all that. Let's just look at the graph and find a point at which the slope is 0. That if we were on this curve, we wouldn't be moving. And I think you could see clearly that it's at the origin. But now let's pretend that we're moving to the right of that point. We're going up the curve. If we were going up a mountain that was kind of curvy like this, the slope would be positive. In fact, the more we go up that curve, the more slopey it gets. So the slope increases positively. Now let's move to the left, but let's start at what we think is the beginning of the curve. Okay, so let's not move left, but let's just move the point left. And then if we follow this curve from left to right, like the way that we read, that value, the height of that point would be going down, just like we would be going down on the parabola if we were falling down it. So at first we'd be falling down quickly, and then as we move closer to that point, 0, 0, then our slope is actually getting less intense or less negative, or our speed is slowing down. Okay, so that means in general there are 3 types of numbers that can represent the slope in this parabola. A negative slope, a 0 slope, and a positive slope. When we talk about a point moving along a parabola, we could generalize that thought to a particle or a body moving through space. And when we think about those things moving through space, we're actually thinking about the position of that particle or the body. And it could be in 3 dimensions, right? X, Y, or Z, or whatever we want to name them. Well, while all that's happening, this particle or body moving through space in all sorts of ways, time is elapsing. And if we want to think about or define velocity, we could relate those two, the position and the time. Now, if we want to define average velocity, we would be thinking about the change in position divided by the change in time. It's the average. How much position has changed and how much time has changed, and let's compare the two. The shorthand notation for average velocity is delta S divided by delta T. In calculus, this is a very fundamental thing, but we take this idea of average velocity and we want to make it more specific to a point. First, let's do an example about average velocity, and then we'll talk about that point. So a car travels 120 miles in 2 hours and 30 minutes. What's the average velocity over the 2.5-hour time interval? So we could do this fairly quickly, but let's have a quick thought about this. Just because a car is traveling 120 miles, it doesn't mean that car is traveling at the same velocity all the time, or same speed. Speed is just the positive version of velocity. So saying that 120 miles is driven in 2.5 hours could mean stops along the way, speeding over the speed limit, and everything in between. Okay. So let's just pull out the information from the problem. 2 hours and 30 minutes. I would write that as 2.5 hours. So let's take the 120 miles, which is the change in position, and divide it by 2.5 hours. I'll leave the units in there so that they could actually show me what the units of the average velocity is. If we divide 120 by 2.5, we get 48 miles per hour. I mentioned instantaneous velocity a moment ago, so let's get back to that. And this is really where the calculus comes into play. So if you have some knowledge about limits, that's great. If not, I think you'll be fine. You just have to accept the notation. The definition of instantaneous velocity is the limit as delta t approaches 0 of delta s divided by delta t. And we don't write the of. This is the velocity at one point in time, the instantaneous, the velocity at that moment, in an instant, right now, right then. My best example of this is when you're driving a car. You know your instantaneous velocity. It's right on your speedometer. It's called speed because you're moving forward. It's always positive. So let's talk about Galileo's question. Let's pose it with him. If a ball rolls a distance of 16 feet in 4 seconds, think about that. That's in a squared sort of way, a relationship that's squared. What's the instantaneous velocity of the ball at a moment of time 3 seconds after it starts to roll? So let's accept the fact that maybe the function is x squared, okay? But we just have 1 point, so we don't really know. Well, we could calculate instantaneous velocity because we know that the ball traveled 16 feet in 4 seconds. So we take the limit as delta t approaches 0 of 16 over 4. That equals 4. But that would be the same value of the average velocity plugging it into the formula above. The problem is that without algebra, we can't do this. There are some other techniques that we could do without algebra using very specific numbers, but we need more data to do that. So assuming that the function would be x squared, we could try this other thing. Let's do this. So at the point 3, that time 3, the function is x squared, so we have 3, 9. So we could calculate just slope between 2 points, right? But let's pretend that the points are the same. So 9 minus 9 over 3 minus 3. That would be slope. y2 minus y1 over x2 minus x1. What happens with that is we get 0 over 0, which normally we would say is undefined because it's a number being divided by 0. But it's weird because that number is 0 on the top. So there are multiple different answers to this question. It could actually be undefined, or it could be 1, or it could be infinity, or anywhere in between. But we need to take a different approach, and that's what we'll do next, an algebraic approach. Fluxions, differentials, ghosts of departed quantities. Whatever you want to call them, we're working with them here. We're assuming that the values of S and T are changing ever so slightly. So let's set up this problem, which is finding the instantaneous velocity of a ball, but using the actual equation S equals t squared. So the setup is the limit as t approaches 3. And let me explain briefly. We're letting t approach 3 because the question is asking about the location 3. So we're kind of approaching it from the right or the left. It doesn't really matter right now. So the same idea is that delta t is approaching 0. And that's of delta s over delta t, which is the same as the definition above. So the limit as t approaches 3, and then let's plug in what these values would be. So instead of using 3 squared for the first value, let's use t squared minus 3 squared divided by t minus 3. So what we're doing here is we're actually plugging in one value for slope, which is 3 and 9, and the other value we're letting it be generic. It could be some value like over to the right or some value over to the left. So like 2.9 or 3.1 or 5.2, but it's approaching 3. What that looks like when we expand is the limit as t approaches 3 of t plus 3 times t minus 3. T plus 3 times t minus 3. And that actually works out. That's so great. And this is one of the examples that helps us in that way. That's the difference in 2 squares. The denominator stays the same. And notice what happens here. Algebra allows us to divide out one of the binomials. So we end up with the limit as t approaches 3 of t plus 3. When there's no denominator in an algebraic expression, especially when with calculus, we can apply a limit really easily. We just plug in. So what happens if t approaches 3? Well then, let's let t be 3. So it becomes 3 plus 3, which is 6. That value right there, my dear students, is the value of the instantaneous velocity of the ball at time equals 3. So what we thought a moment ago, which could possibly be 4, the number 4, and then we thought maybe it's undefined, well then maybe it's 1, or it could be infinity, or everything in between. It's actually 6. In the next video, we'll expand on what we just did using 2 different approaches. A great follow-up, though, would be to do this activity. I invite you to try it. I like it. Well, thank you so much for watching. I hope you learned something, and I'll see you in the next video.